Hello everyone. Today we're going to be talking about enthalpy of formation. The symbol for enthalpy of formation is delta H with a little f, as you can see here. It is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. If you'll notice that there's a table, and this can be found in the appendix of your textbook, there's a small list here provided for you that has the enthalpies of formations for various elements, compounds, and you'll notice that all of these variables or all of these values have been taken under what is called standard state conditions. You'll notice that there's a little degree sign here. And all that means is that these conditions are specific to temperatures of 25 degrees Celsius or 298 Kelvin and the pressure being 1 atmosphere. So whenever you see that little degree sign, it means that these measurements were taken under those conditions. You'll see the table has numerous examples of delta H's of formations. Your appendix has a more extensive list. Now, let's put this into practice. They're going to ask you here to write an equation demonstrating the heat of formation for a compound. Now, the rule is this. In order to set this up, you must write the reactants. The reactants have to be the elements that make up the compounds, and it must be written in their natural states. For instance, if an element is like oxygen, which is diatomic, you have to write it as O2, and naturally it's a gas at standard state. If it's a metal, okay, metals are going to be solids. The only metal that's a liquid at room temperature would be mercury. But the key is when you set this up, it must be equal to 1 mole of the compound. If you look at letter A, the compound that we're trying to create is magnesium carbonate. So the elements that make up magnesium carbonate are magnesium, and magnesium normally is a solid at room temperature. The second element that makes up magnesium carbonate is carbon. Now this one is tricky. For carbon is a solid. However, there's two forms of carbon. There's diamond and graphite. So you have to specify whenever carbon is involved, which one. So we're going to put here that it is the graphite form. Okay? And then the final element, let me fix this up here. The final element is going to be oxygen, and that one's diatomic. So you put O2, you put a gas, and then what you're going to do is you're going to equal it to the product, which is magnesium carbonate. Now notice it has to equal to 1 mole. All right? So you're not allowed to touch the product. The product has to stay as 1 mole. Right now, it is 1 mole of magnesium carbonate, but it's not balanced. So in order to fix this, you have to balance the reactants. Now, the magnesiums are okay. There's 1 on each side. The carbons are okay. There's 1 on each side. However, look what we got to do here. We got to fix the oxygen. You want to have 3 on that right side. So notice there's 2 on the left. Here you're allowed to use fractions if needed. If you put a 3 over 2 here, okay, 3 over 2 times 2 is exactly 3. By putting that 3 over 2, you have now finished balancing this. Now, if you look at a table and they ask you what is the delta H of formation value for magnesium carbonate, this is from a table. You could find this either online or in the appendix. It is 1095.8. The units are kilojoules per mole. Okay? Now, we're going to do a second one. If you'll notice, the second one is to form glucose. So, the elements, and of course has to be set up as 1 mole of glucose. So the elements are going to be carbon, and the carbon again is going to be the graphite form. So you're going to put carbon as a solid, graphite. The second element is hydrogen, and you'll notice hydrogen is a diatomic element and it's a gas. And the third and final element is oxygen, which is also diatomic. and a gas. And then what we do is we're going to equal that to 1 mole of glucose, which is a solid. Now remember, we cannot touch the right side. It's already 1 mole. So what we must do is, in order to make the left side equal to the right, notice that there are 6 carbons here. So we're going to put a 6 here in front of the carbon. The next thing we're going to do, if you look at the hydrogens, okay, there's 12 over here. So if we put a 6, we now fix the hydrogens as well. And then we're going to put a 3 here in front of the oxygen, and that would make everything balanced. Now the delta H of formation for glucose, and this again comes from a table, is negative 1,273.3 kilojoules per mole. Okay, so these are the first 2 that we have. I have 2 more examples that I'm going to show you. If we go here, these are the next 2, and these are found on the Chapter 5 PowerPoint. The first one is to write an equation finding NaCl. Okay, so let's do letter A here. And again, what we're going to do is we're going to set up the elements that will give us NaCl. So sodium naturally is a solid, and chlorine is a diatomic, and chlorine normally is a gas at a room temperature. And then what we're going to do is we're going to set that up to NaCl, 1 mole of course. Okay, and then the only thing we got to do here, if you notice, the sodiums are okay. There's 1 on each side, but there's 2 chlorines on the left. So what we're going to have to do to make it 1 is put a 1/2 here, and that will be the answer to this one. And again, we're going to go and find the delta H value of formation for NaCl from a table. And this one, and pay attention to the states of matter, because the table has one that's NaCl aqueous, another one gas, and another one solid. We want to pick the correct one, which is the solid, which is negative 410.9 kilojoules per mole. And then we have one final problem. Our last one here is making lead nitrate, and this one has 3 elements. Okay, so first we're going to put lead here, and lead is a solid at room temperature. Then we're going to add it to nitrogen. Now nitrogen, remember that nitrogen is diatomic, so set it up as a diatomic. It's a gas, and so is oxygen. This one's also a gas here. And we're going to set this up so it's equal to lead nitrate, just like this, as a solid. Now, if you notice, we already have 1 mole of lead nitrate, so we're good there. What we're going to have to do now is we're going to go and balance the elements like we did with the previous ones. Well, let's take a look here. The lead is fine, okay? There's 1 lead on each side. Now, notice nitrogen is fine as well. If you look here, there are 2 nitrogens here and there are 2 over here, so don't touch that one. Now, this problem has 6 oxygens, so there's only 2 on the left. So if we put a 3 here, that will fix our oxygens. And then what we're going to do is we're going to go to the book again, okay, to the appendix, and we're going to look for the lead nitrate as a solid and write the delta H of formation value. Okay, and according to the book, it is negative 451.9, and it is kilojoules per mole. So this is how you write a heat of formation equation. You set up the element, you set up the elements that give you the compound, but the compound must be 1 mole of a compound. And the elements must be in their natural states, okay? So if they're diatomics, you must make them diatomic and put the correct state of matter. as you set it up. Okay, so this will conclude our lesson. Our next lesson will be on calculating using delta H of formations to find the delta H for a reaction.